So now we can finally apply the inverse function theorem to capital F at x0, y0. And it tells us that there is some open neighborhood of x0, y0, let's call it U, such that, and then it tells us three things, right? And I'm just going to use the numbering in my statement of the inverse function theorem before, except I don't want to confuse 1, 2, and 3 here with the... So back here at the very start, in the statement of the implicit function theorem, I numbered the conclusions of the implicit function theorem 1, 2, and 3, and I don't want to confuse with those numbers. So down here, let me call these 1 star, 2 star, and 3 star. So the inverse function theorem can be applied to capital F, and it tells us that there's this open neighborhood U such that if I use the name V for capital F of U, the image of U under capital F, then that is open. So it's an open subset of Rn plus m. Secondly, if I restrict capital F to U, then that's going to be a function from U to V, and it's going to be injective. So since V is by definition the image, bijective. This is a bijection. And 3 star is telling us about differentiability. So F restricted to U, well, it's invertible as a function of sets. So this is the inverse. So that's not saying anything new that 2 star isn't saying. But is a C1 map. That's what 3 star says. So continuously differentiable. And I'm actually going to add a couple of other things here that the inverse function theorem tells us, but not as much directly in the way we stated it. And probably I should have included these when I originally stated the inverse function theorem, but they are things that we proved while proving the inverse function theorem. And they are things that you can deduce from the inverse function theorem in the way we stated it without too much difficulty. So they are the following. So 4 star says that F restricted to U prime. So in the statement of the inverse function theorem, we assume for the inverse function theorem, we assume that F prime is invertible at x0, y0. Right? That's what we needed. That's what we worked so hard to prove up here. So the inverse function theorem has an assumption of invertibility of f prime at one point. But what it provides is invertibility of f prime actually on the entire neighborhood U of that one point. So I don't know why I'm writing, I don't need to write restricted to U, I can just write f prime is invertible. F prime of xy is invertible for all xy in U, rather than just what we had up here, which was just for specifically x0, y0. So this is something we had actually in the proof that we gave of the inverse function theorem, but we never wrote it as a final conclusion in the theorem statement. You can infer it afterwards if you want to. You need to know that, possibly you might have to shrink the open set U in order to guarantee this. Well, no, I guess you can infer it from the chain rule. Yeah, you can infer it from the chain rule. If you didn't state it in your original inverse function theorem, just because you know, f, yeah, actually this was one of the presentation problems. So you've seen, you can infer this from the chain rule. From knowing 2 star and 3 star, knowing that f is a bijection and its inverse, you know, when you restrict to u, it's a bijection and its inverse, and f is differentiable at C1 and the inverse is C1, then you can use the chain rule and look at a composite and be like, okay, the linear approximation has to be an invertible map at any point. Okay, and 5 star is I just looked it up in my notes. What I need here is a statement about the derivative of the inverse. So if I take this derivative, which I'm saying exists in 3 star, and this will also be the chain rule. It's that same presentation problem. So this at, let's see, f of xy, the derivative of the inverse is the inverse of the derivative, is take the derivative of f at xy inverse. And this is for all xy in u. So this is another thing that we proved while proving the inverse function theorem, but I think I never stated it as a conclusion of the theorem in the theorem statement. Okay, so this is what the inverse function theorem tells us about capital F. Yeah, so our goal, I guess, is to define, let me go back to the statement of the implicit function theorem. We've used these assumptions now, and we've used the inverse function theorem and gotten an inverse for capital F. Our goal is to define this function capital X, which is going to be a function of little y, and what we want is for capital X, for given any little y, we want capital X of little y to be to end up being the unique value of x that can be paired with y in order to have the f of them be 0. So let's think about how we can do that. Okay, so thinking about what we have here, that f restricted to u is a bijection from u to v. So let me try to visualize what we have. We have u to v, and f restricted to u is a bijection. So things in u go to things in v. And things in u I can think of as an x part and a y part, right? So things in u will be n plus m tuples, which I can think of as an n tuple x part and an m tuple y part. And they're going to be mapped to things in v. Specifically, the way capital F works, so going back and looking at the definition of capital F, is the first part of the output, the first n components of the output, are actually just little f. So let me make some more room for that. So here you just get little f of xy, which will be an n tuple. And then for the second part, you just get y, right? Capital F just basically does what little f does, but then it also tries to remember what y was. So this is the function that we have now successfully inverted. This is the function that we have now shown is a bijection on u. Now, our goal is to define that function capital X. So our goal is to, in some sense, go backwards. But let's try to explain how, in what sense exactly we're going backwards. Our goal is to find for each y, for each choice of y, we want to find a choice of x, and hopefully the unique choice of x, that makes things so that f of xy is 0. So given a y, I want to define the unique x that makes this come out to be 0. So what I want to do is start with a given y here and pair it with 0, and then figure out what x would be associated with that. So take this arrangement and go backwards and look at the x here. So that's the goal, and we can now do that since we have inverted this function. We can say, okay, what x would get sent to 0 y? Whatever that x is, that is going to have the property that it, when paired with y, makes this 0. In other words, x and y satisfy the list of equations that little f is specifying. So you see the utility of and the importance of defining this function capital F that remembers what y was. So capital F is just like little f, but it's remembering what y is, and that is what enables us to have something to go back with when we invert it. We can start with the little y and then use that on our way backwards as we go along the inverse. So that is my attempt to motivate the upcoming definition. Okay, so first, I'm about to say define x from w to r. So it's going to take y's and give you x's. So it's going to output x's. So soon, in a moment, I'm about to say define x like this by x of y equals, and then I'm going to basically do what I described here. Take f restricted, capital F restricted to u, and then take the inverse of that and apply it to 0, comma y, and then take the first component of that. First component of this. Okay, so I'm about to write it down more properly in a moment. But first, what is the set W? I have not defined that. So first I want to define the set W. It's going to be the set of y's that I can apply this inverted f to. So W is going to be the set of y's in our M such that, so which y's can I apply the inverse of this function to? Well, those y's, no, I don't mean apply the inverse of this function to. Which y's have the property that I can apply the inverse of this function to this pairing, 0, comma y? Well, it's these y's, such that this is in V. Like that. So that will be W. Those y's that when paired with 0 like this give you something in V. Okay, now I can start talking about defining x. So capital X from W to Rn. So I could describe it in terms of, so I'm trying to describe this red mapping basically. And I could describe it in terms of components. It would look like this, but this is going to be kind of ugly, so I'll come up with a better way in a moment. But here's what I would say, just writing out all components. If I apply capital X to y, then I want that to be the following n tuple. So I'm going to go down and list the components of what I want to come out. First, take f restricted to u inverse and apply it to 0, y, and then take the first component of that vector, of that vector. So just this portion, this will be an n plus m tuple. It'll be something in U. Take the first component. That will be a real number. Then take the second component, then the third component, and so on. And then stop. Even though there are more components, stop short. Stop at the nth one. So that's a way of putting it. I'm going to clean this up a little bit in a moment. So that's our definition for x. Here's a way of cleaning it up. So I'm going to define some projection maps. These will be really useful later on, probably. So I've already mentioned projection maps pi sub I earlier when I was doing stuff up here with figuring out the partials of capital F. I think, over here I was like, okay, capital F, sometimes some of the components of capital F are just projection maps. I don't want to confuse the new projection maps that I'm going to write down with these ones. So forget about these for now. I'm going to use a notation now for some new projection maps. And maybe to just avoid confusion, I will use this notation. So define. So let's see. I'll use the notation pi superscript 1 in parentheses. That should be something that you will not confuse with pi sub 1, pi sub 2, up to pi sub n plus m. Those were our earlier projection maps. Now I'm just going to define two projection maps, pi superscript 2 in parentheses, and pi superscript 1 and pi superscript 2. And they are going to be the following kind of map. So both of them are from n plus m. But the first one selects the first n components, and the second one selects the last m components. So if I use that notation that I've been using, where I write down an n plus m tuple as a pair, then it's really easy to say what they are. Okay, so then it's very easy to describe what is x. X is, well, just take f restricted to U inverse. So x of y is going to be take f restricted to U inverse, apply it to 0, comma y, and then take the first portion of that, the first n components of that. So that is our definition for capital X. And let's see, are we done setting up what x is? So where are we right now? Here's our implicit function theorem statement. I have defined u, and u is open. That was part of what the inverse function theorem said. And I've defined w. I still need to convince you that w is an open neighborhood of y naught. And I've defined x. And then I need to prove 1, 2, and 3. So it remains to prove 1, 2, and 3, and also to prove that w is open. Okay, so why is w open? This was the definition of w. So let me actually make some extra room here. Move this stuff down, and then I'll talk about why w is open right after I mention w. So actually I need to convince you that w is open and that it contains y naught. So w is an open neighborhood of y naught. So let's start with containing y naught. Why does w contain y naught? So for y naught to be in w, I need 0, comma y naught to be in v. So yeah, so let's just start saying it. We have 0 y naught in V because, okay, so this is often a strategy I take. Start saying that we have something and then stop and think, why? Why? So for 0 y naught to be in V, it has to be capital F of something in U. And it is. 0 y naught is, another way to write 0 is f of x naught y naught, right? Since we assumed at the very beginning that x naught y naught satisfy the equations specified by f. And this is capital F of x naught y naught. And x naught y naught is in U. That is part of what we got from applying the inverse function theorem. U is a neighborhood of x naught y naught. So, oh, sorry. So y naught must be in W. Okay, good. And why is W open? So I think W is open because V is open. And W is the preimage of V under some mapping. So W is the preimage of V under a certain mapping that I hope I can show as continuous. So W is the preimage of V under what mapping? The mapping y goes to 0, comma y. So that's a mapping from Rm to Rn plus m. This is the embedding. Y goes to 0, comma y. So you see how W is the preimage of V under this map? It's the set of points in the domain of this embedding that get mapped by the embedding into V. So yeah, the preimage of a continuous, the preimage of an open set under a continuous mapping is open, and so W is open. Okay, but why am I saying it's continuous? So why is it continuous? Well, here's an easy way. It's linear, and we've proven that linear maps are continuous. Right, this is a vector space embedding. This is a linear map. Okay, and this map is going to come up again and be useful. So actually, now that I have defined these functions, pi1 and pi2, these projections, let's also go ahead and give this map a name for later use. Since I've mentioned it now, I think it's a good time to define it. So define, okay, so this embedding, I'm going to call it, so this embedding sends an m tuple to a vector that goes 0, comma, and then that m tuple is the second component. So since it ends up being the second component, I'm going to call this embedding iota superscript 2 for second component. So I'm going to define maps iota superscript 1 and iota superscript 2 as being the inclusions that you can think of as sort of going with these projections. So this one will be Rn, to Rn plus m, and this one will be Rm to Rn plus m. And they will just be these maps. Iota 1 of x will be x0, and iota 2 of y will be 0y. So v here is w here is the preimage of v under iota 2, and these iotas are linear and so continuous. Okay, great. So let's summarize where we stand now. Here is my implicit function theorem statement. I made all of these assumptions. Then we have now verified that there exist u and w open neighborhoods of what they need to be open neighborhoods of, and defined x. And what we need to do, now that we've defined u, w, and x, is prove all this junk here. So let's proceed with that in the next video. And remember those functions iota and pi. Those will be useful ways to talk about the somewhat complicated relationship between, I mean, not complicated relationship, but usually complicated to talk about relationship between little f and capital F.